memes?
Of course.
Yes.
They actually are.
Okay. I mean, I'm not going to follow it. You guys can say no. That's great. There's been quite a few under the radar ones that have not been so good. All right, let's stop with all the social media stuff. We already paid too much attention to it. Anyway, here we go. The recorder is started. Oh, you're being microphone. Anyway, here we go. Is that a verb? I don't think so, but we should make it one. Okay, yesterday, did we talk about how to use our calculators in spiffy ways? Okay, that's fun. Yes. Yes, we did. We went to sequence mode, remember? And in sequence mode, we talked about how there's this whole thing called recursive. Now, we didn't really get that into it, but recursive programming that allows us to say, hey, you're not smarter than I am, but faster than I am, right? Computers are faster than I am, faster than you are. As far as it can add 100, 5,000 terms, oh my goodness, the wheel is turning, but it's doing so much math, so much quicker than we can. Anyway, we saw that. That's the recursive thing. That's the really cool, like using a computer thing. Kind of hard to write down, but not too bad if you understand that you can say, hey, you, my current term, I can talk about the pattern that's happening to my previous term and make you do all the jumpity jumps. The most famous of that one is, oh, fun. There's so many online. Okay, I can have fun with this. Anyway, there's really cool Fibonacci sequence videos also. We can have some fun with that. Which, in some ways, someone this morning was like, Mr. Horn, how is it going to do online? I'm like, guys, think about it. Like, teachers totally get to say, we get to take class time, or you get to have an assignment where you get to go play and hopefully have your imagination sparked with cool things in our subjects, which is kind of fun. Which, in like the daily grind and the, oh my goodness, test calendars, and we have to get all this fit in, like sometimes we don't get to have quite as much fun. And you guys being distracted and us being slowed down, we don't always get to have as much fun either.
So how are they going to do with it?
Because you can have, like, think how you guys submit pictures of yours. They can submit pictures of the stuff they're doing from home. He has like a wood burning group. I mean, the ceramics is going to have to be a little bit more creative, but think about how they could be exploring different techniques and different artists out there and there are ways to not be doing the same thing as they would in class, but to still be interacting with the material in cool ways.
Okay.
Anyway, all I have to say, all of us are having to think way outside the box, and Mr. Horn this morning was like, oh, no, I have a plan. And then, like, Coach Johnson's like, okay, yeah, that's awesome. Anyway, so they're thinking.
Coach Johnson be asking for 30-minute videos, though.
Okay. So factorials. Alec was mentioning about how we were at the beginning of the year, you guys were, without me. So sad. It's one of my favorites, even though it's kind of old and it's kind of, but still, it's like CGI came from math and an old math book that someone just unearthed and said, hey, I can use this in new ways. That's kind of the crazy thing about math. Started with philosophers way back when, just asking themselves big questions about life, and then just kind of that going in a few centuries later, being like, that can be used for this, and then a few centuries later, that can be used for this, and then all of a sudden it leads us to all the technology craziness that you have in your hands. And the cool movies that you love to watch and have all these like things that aren't real but seem like it. Anyway, fractals are cool. But Fibonacci sequence, there's some cool stuff behind the scenes in that, but we're not going to spend time today on it because you have me in front of you. Let's use this time well. Factorials is what we were talking about with fractals. The weird thing is that 0 factorial is defined to be 1. There's actually a proof of it. It's been a long time since I've seen it, and it's actually pretty easy if I remembered how it goes. It's just never off the top of my head for whatever reason. Hey, but what's something else that, I could show you how this one works a little bit easier, but what's something else that has a 0 in it that we kind of just need to memorize? Maybe with 1s and 0s. That's actually really impressive because matrices, not many people would use that one. Let's go back to like way middle school math. What's something with a 0 in it that you kind of had to memorize? Exponents. Yeah, what's anything to the 0 power? 1. Okay, that's the easiest illustration. Anything to the 0 power is 1. I mean, I could bring in ln, but ln of 1 is 0, and then you're going to get all messed up. So anything to the 0 power is 1, 0 factorial is 1. Cool. With factorials, especially in Calc BC, which I know most of you is not on your radar right now, but it might be one day. The best way to think about factorials truly is to start at 1 and count up, which I know isn't your favorite because most people, when they learn factorials, 5! Nope, just kidding. 5 factorial is 5 times 4 times 3 times 2 times 1. That's how a lot of people would talk about what this is. But technically, the better way to think about it, especially because variables start showing up in factorials as we get blessings. It's rainy and allergies, we'll just say that. Variables will start showing up in factorials, and if there's a variable in a factorial, if you have to start at what the number is, if I had to start at n, I don't know who it is. So what's before? I don't know. So we start at 1 and say, okay, what's before n? I don't know. 1 less than n? What would be before n minus 1? I don't know, I guess n minus 2? What would be before n minus 2? I don't know. Yeah, I don't know what the number is, but I know how to tell you how to get there. Just take away 1, just take away another 1, just take away another 1. Anyway, so this is kind of the better way for future math. But let's talk about the difference between these two, because they are not the same thing. And you guys should see that because of parentheses, but at first glance you might not realize it. If I start at 1 for both of these, assuming that I keep going beyond 3, question. Where does this one end?
You don't know because they're variables.
But how could I mark the ending? Nope. The difference. This one says whose factorial? 2n's factorial. Where am I ending? 2n. This one says 2 that doesn't have a factorial times n that does have a factorial. See the difference? Which one would be bigger or stronger? This one?
No, the one above.
This one. Because this one is saying I'm double, right? You guys are wrong. He's so much stronger. Why is he so much stronger? This guy's double, 1 to n, that's 2n. What's the big deal? Pause. What if this was 10? It'd be 1 through 10 times a 2. Wouldn't this one be 1 through 20, aka 1 through 10 times 11 times 12 times 13 times 14 times 15? That one's only times 2. Remember, parentheses, this is not being distributed. There's no addition or subtraction. This is actually the same thing as saying, hey, I'm doing 1 through n and a 2. Whereas this one says, let's go 10, 11, 12, 13, 14, 15, all the way to 20. Anyway, as far as which one is stronger, this one is way stronger. Sorry, I'm introducing all kinds of Calc BC stuff right now. Not super important for right now, but this is probably the first time you've ever seen a variable with a factorial. And hopefully for most of you, it's not the last. So, let's see. What if they give you something with a variable and a factorial, but you don't have to leave the variable there? They say, no, it's okay. Go ahead and plug in. Go find me some terms. This is an nth term formula, 2 to the n power, all over n factorial. What if they say, find me the first 5? How do I find the first? How do I find the second? How do I find the third, the fourth, and the fifth?
You can just plug it in.
Huh? Oh, because we're counting up to a factorial. Even though most people think of it counting down, counting up is actually a bit more effective, especially if you have a variable.
Would you, like, that's what it looked like if it was a variable, or the n is supposed to be a number right now?
The n is representative of the variable end that I don't know until they tell me what it is. So this one says 2n factorial is 2, just the number 2 times n's factorial. N's factorial is 1 through n times, I don't know, an additional 2. Which isn't near as strong as saying, hey, 1, 2, ooh, go twice as far to go all the way to, instead of like 1 to 10, go 1 to 20. This guy's way strong.
So you're saying n is like 10 or something, but you don't know. Okay.
Right. Okay, over here, if I'm finding the first 5 terms, how do I find the first term? Yeah, it's just one of those nice little plug-it-in ones. So, plugging in 1, I get 2 to the 1 all over 1 factorial. And then I get 2 to the 2 over 2 factorial. And then I have 2 to the 3 all over 3 factorial. Then I have 2 to the 4 all over 4 factorial. Then I have 2 to the 5 all over 5 factorial. Right? Although, come on, we're good math students. Should we leave it all that?
No.
Messy? Nah. Now, it will be a helpful skill, especially in Calc BC, to have some of these factorials memorized. Let's talk about a few of them. We know 0 factorial is equal to what? 1. What's 1 factorial equal to? 1 times, you don't go any higher, right? Just 1? What's 2 factorial? That's weird, they're the same thing. 1 times 2 is 2. What's 3 factorial? 1 times 2 times 3 is 6. Isn't that the same thing as just multiplying him by 3? So 4 factorial, 1 times 2 times 3 times 4. Wait, 1 times 2 times 3 times 4. Wow. You just have to multiply. We haven't simplified yet, Sophia. I'm just talking about how it might be helpful to have some of these basic factorials memorized eventually. Not really this year, but eventually. If I want 5 factorial, isn't that 1 through 4, which is times 5? Oh, that's 120. Hey, 6 factorial is 1 through 5 times 6. Oh, that's 720. 7 factorial. Oh, that's 1 through 6 times 7. That's not. That's no fun. Okay, so some of the basic factorials. It's kind of nice to have those numbers in your head eventually. In a couple of years, maybe. All right. But if I was to simplify, can't I make this just 2 over 1, which is 2? Or 4 over 2, which is 2? Or 8 over 6, which is 4/3? Or 16 over 24, which is 2/3? 8 goes into 16, 8 goes into 24. Or we have 4 and 4 is 16, 32 over 120, which ends up being 6 doesn't go in, 4 goes in, 4 goes in, nope, what is it? Yeah, 4 goes in, 8 times, 8 over 30. We can keep going then, 16 goes in, oh, 2 over 5? Oh, 15. Then we're done? 4 15s? Sorry, Sophia, what's up, kid?
Why is a 1 not 0 or 2 to the 0 and 0?
Because I'm silly and I forgot to start with a sub 0. I'm too used to starting with 1. So then 0 would have been 2 to the 0 over 0 factorial, which would have been 1 over 1, which is 1.
And then you got out to a 5.
Oh, because it says find the first 5 terms? Nice. Which makes it a little interesting because then if we start with 0 to get the first 5 terms, we end at a sub 4. It's a little weird in our minds, yeah? Mm-hmm. Speaking of weird in our minds, what do we do if they tell us to simplify factorial expressions? Wait a minute, we stopped at 6 because it started to get real gross. We're going to really go to 8 in our heads?
Calculator.
Someone think creatively. What is 8 factorial?
Oh, let's see. 8 times 6 times 7 times 8
Isn't it just 42 times 8? Or 56 times 6? Right? 42 times 8 or 56 times 6 or 48 times 7, whichever one you think is easier. Oh, you're still going to your calculator? Okay, where is the factorial?
40,000.
Oh, but if you want to find the factorial, I mean, you could just do your like 1 times 2 times 3 times 4, but there is also a math probability. Ooh, that's the chapter that we're in. Number 4. Hey, look, there he is, that really excited number. But I think some of you guys might also in your shortcuts, do you have a factorial hiding? Yeah, number 9. Some of you, it depends on how updated your calculator is. Some of you have it in the alpha window shortcut. He's chilling down there. But you could also do one more time, math probability.
Is there a way to edit like that thing to use it first?
I don't think so. It'd be nice if it was. I don't know. I was searching like a TI, since we have extra time now, yeah. Help desk or help board and see what they say. Customer care thing. I don't think so though. 16 and 1 is 336. Nope, because I already got rid of that. I only had this left over after.
Put the thing on the bottom.
Oh, did I not press that button? 1. Uh-oh, my lines were crooked. There's 1, there's 2, there's 3, there's 4, there's 5. There you go. What's really weird is if you have to do this and you're like, I don't know, but yes, you do. Don't you know that this guy goes all the way up to n, which means n minus 1 is before him, and n minus 2 is before him, and he goes all the way up to n minus 2. What's left? 1 over n minus 1 times n. And I know for you right now, this isn't going to seem to have any practical application whatsoever with the weird n's. Just trust me, where I know you're going, it does. Sigmas! That's on the SAT, which is probably been canceled. Anyway, so, sigmas.
Cancel the lap test.
No, because then you don't get college credit for your entire year. I'll just take it for the summer. Please say no. Coming back, zooming in. Sigmas. Sigmas. If I'm adding A1 through, I don't even know what. A sigma says, here, give it all to me and I can do it, and I can do it all at once. And your calculator says, ooh, and I know that sigma guy. That alpha window, see your sigma? He says, give me whatever you want. You want to add together all these A's? Well, just have a formula for it. Plug it into me. Tell me how many you want to add. And you do not have to type it all out. A sigma notation basically takes this huge sum and says, give it all to me. If you can find a pattern that matches or fits them all, hence the practical application of finding an nth term, because it summarizes it all. And sigma, remember, says, okay, plug in 1, plug in 2, plug in 3, plug in 4. It counts by integers all the way up to find the first 10, find the first 100, find the first 1,000, however many you need. However many you need. And in calculus, there's a thing called an integral that is defined by a sum, an infinite sum, a sigma. And so that's another practical application that someday you'll see. But what's really nice with sigmas is even though it can all condense down into one big one, if there's something like a constant by himself, like a 2 or a 3, it'd be 2 plus 2 plus 2 plus 2 plus 2 plus 2. However many times you have 2's, you can actually take this sigma of a constant and make it c times. It'll be, remember, multiplication is repeated addition. Repeatedly adding a constant just gives you n of those c's. That's a nice little like, hey, I can get rid of the sigma with a formula. If there is a constant, I can pull it out and say, let's just do sigma of this and then times this at the end, because this would be n, c can be factored out. Or a plus b, a plus b, a plus b would be the same as a plus a plus a plus b plus b plus b with like whatever subscript it was that you're adding. Same thing with subtraction, except I just need to keep those negatives with all those b's. But there's some cool properties of sigmas that might not really mean much to you, but are super helpful in the future. But what I want you guys to see is you can totally put this in your calculator. Please take your graphing calculator home. That would be something that would be hard to recreate. Please take your graphing calculator home. Please take your book home. Yes, I can email you a big old honkin' PDF version that probably wouldn't open on a phone or on a device, but you could download it to like a laptop or a desktop. If you want it, you can email me. I'll send it. But just take your book home. Take your grapher home. Take your comp book and your homework spiral home. You could put it in your grapher. You could. But I also want you to make sure that you know how to do it if you were to need to do it by hand.
Oh,
But is it though? This one's actually kind of easy, because isn't it just, can't I just pull out the 3 and say, isn't it 3 times 1 plus 2 plus 3 plus 4 plus 5? Wouldn't that be 5 plus 5 is 10 plus 5 is 15, 3 times 15 is 45? Woo. Some of you would still be looking for the sigma in your calculator. No.
my sigmas look like they got a new car crash.
This one, I could go ahead and add the 1 plus 3 squared, 1 plus 4 squared, 1 plus 5 squared, 1 plus 6 squared, or I could just do, oh, how many 1s am I going to do? Well, 1 for him, 3 and 4 and 5 and 6, right? I'm going to have all of those, and I'm going to have all of these. I'm not sure if it makes it way easier, but it is another way of looking at it, splitting it up step by step or piece by piece. What you can't do is take a squared out. That's illegal. Poor little puppies. There'd be a whole bunch of them, I tell you that one. Keep that squared in. You would have to go ahead and do it step by step, but eventually, I have faith you guys could get there if you needed to by hand and weren't too lazy or fall asleep in the middle of it. Or have someone tell you a good joke in the middle of it. So you have to be ready more than anything else. The last thing is, what if there's no ending? There's an infinity on top. What if there's an infinity on top? If there's an infinity on top, then we just keep going, plus dot, dot, dot. So what's going to happen if it says find the third partial sum and the sum? If you ever have an infinity, oh look, the next page is homework from my dad. If you ever have an infinity on the top of your sigma, you can start writing this out. And the third partial sum says sum, third, take the sum of the first 3 terms. I could plug in 1 and I get 3/10. I could plug in 2 and I could get 3/100. 3 over 10 squared. I could plug in 3 and get thousandths. Well, I don't know what that is. Yeah, you do. Isn't that 0.333? What would the infinite sigma be of adding all of these, infinitely many of these together? What? So what's going to happen if you add another and another and another and another and another? 0.33333333333333333333333. The infinite sum is a constant, finite, itty bitty number that it would take forever to add it to actually get there. Muy interesante. Does that mean every infinite sum will always be a number? No. But we're going to have to wait to see more infinite sums until section 9.3, and then we get to talk about the idea of a limit, which is where calculus starts. Alright, cool kids, homework is due on Tuesday morning at 8 a.m. just to give you, I don't know, if you want to take it, you can take it. If you want to procrastinate until Monday night, I guess you could do that. But I will go ahead and post on Monday section 9.2 information with the homework probably due Thursday morning at 8 a.m. Sound good? If you need something, comment. Or group chat and have someone reach out to me.
I'm just gonna give you a call.
Sure.